Just to give you some idea of what the apparatus actually looked like, here's a replica of the Crookes tube used by J.J. Thomson at Cambridge University in England. If you look at this apparatus, you can see on the far left end basically areas for evacuating the tube and for leads to come in, little wires to come in, both to create the cathode rays, and then over here to apply voltages across the plates to deflect them. At this far end is the tube, or the bubble on which one could see the spot from the deflected electrons. Now that Thomson measured the charge to mass ratio of the electron, if physicists could figure out either the charge or the mass, they would know the other quantity. Thomson and his team made an attempt to measure the charge on the electron. They did this using water droplets suspended in an electric field, and we'll come back to this in a few slides. Using this method, Thomson found a value of 1.03 times 10 to the minus 19 coulombs for the charge on the electron. But we know from earlier on, not that that's the key here, that the charge on the electron is actually closer to 1.6 times 10 to the minus 19 coulombs. Clearly a very large error, and they were aware of these errors. Thomson had the right order of magnitude, but the error that he and his team and subsequent teams got was unacceptable. So it wasn't until about a decade later, in 1909, that a graduate student refined the technique that Thomson and other teams had been using in order to finally get an accurate measurement of the electron's charge. Although this graduate student built on many years of experimentation by other physicists, he refined the technique in an afternoon. But even with his clever new approach, it still took months of tedious, careful experimentation and calculations before the much more accurate value for the charge of the electron was found. The idea was straightforward, but first let's consider how Thomson and others approached the problem. How can we find the charge on an object? Well, we did some problems like this earlier on in the electricity units. We know that a charged object will fall with a constant velocity if its weight is balanced by an upward electric force, just as is shown here. mg being the weight and Q times E being the electric force. It would be nice if we could use this technique of balancing weight and electric force applied to the electron to find its charge, but we have a few little problems. One is we can't see the electron, and we don't know their mass. So Thomson and other physicists attempted to float charged water droplets in an electric field. In this way, with an estimate of the droplet mass and knowing the electric field strength, they should have been able to calculate the charge that was on each droplet. But the experiment had a major challenge, and one that made accurate measurements impossible. Water droplets evaporate quickly, and as they do, their diameters, and so their masses, diminish.